Have you ever looked up at a night sky full of stars and wondered how old they are? Or maybe you've seen an ant colony and wondered how many ants there are in it. Well, in both cases, we can appeal to a powerful mathematical tool that allows us to count the uncountable infinity. Hi, I'm here with Minute Earth. Let's start with those ants. You might think counting them would be impossible, but mathematicians have been counting the members of infinite sets for centuries. So counting ants is no sweat. The key is to realize that even though there are lots of ants in an anthill, there aren't actually that many different types of ants. There's usually just one queen per colony, and all the rest are her daughters. And each ant has only so many possible roles in the colony, like egg layer, nurse, soldier, or forager. So if we count the number of different types of ants, and then figure out how many of each type there are, we'll know how many ants are in the whole colony. We can use the same strategy to count the stars in the night sky. The first step is to identify the types of stars we are looking at. Astronomers don't classify stars based on their appearance, but rather by their luminosity, or how much light they give off. Stars fall into a few dozen categories depending on how luminous they are. And once we decide which types of stars we want to count, we can use math to figure out how many there are. That's because the brightness of a star tells us how far away it is. See, stars are so far away that they look like pinpoints of light. And since we can measure how bright a star looks from Earth, we can work backwards to figure out how far away it is. With this distance, we can then calculate the star's luminosity. Once we know the luminosity, we can calculate its absolute magnitude, which is how bright it appears from 10 parsecs away. By comparing the absolute magnitude to the apparent magnitude of other stars of the same type, we can determine how far away they are. So if we're looking at a cluster of stars that are all the same type, we know exactly how far away they all are from us. Now, if we take that distance and cube it, we'll get the volume of space that those stars occupy. And from that, we can calculate the number of stars within a certain radius of the sun. And from there, we can extrapolate the number of stars in the entire universe. Of course, scientists are constantly refining these calculations as we learn more about the universe. But the basic idea is the same as counting ants. We identify the types and then use math to figure out how many of each type there are. And it turns out that there are as many stars in the universe as there are grains of sand on all the beaches on Earth, 10 to the 18th power. That's a 1 followed by 18 zeros. But really, that's just a rounded off estimate. In reality, there could be anywhere from 10 to the 27th power to 10 to the 30th power stars in the observable universe, somewhere between 100 trillion and 1 quadrillion. And if that sounds incomprehensibly huge, well, that's because it is, but it's still finite. That means there are only that many stars in the universe, which isn't very surprising. After all, the universe is only so big. But what about the real infinite? George Cantor wondered if there were even more infinities between those two. Like, could there be an infinite set that was bigger than the set of all the stars in the universe? To find out, he turned to something a lot closer to home. Real numbers. Say you're trying to find the value of pi. You might start by noting that pi is the ratio of a circle's circumference to its diameter. If you pick any two real numbers, there will always be another real number between them. And as you continue to try to pin down the value of pi, you'll find that you can always squeeze in another real number between the two you've already identified. It's like trying to nail a moving target, and that means there are infinitely many real numbers between any two real numbers. But since there are only 10 to the 30th power or so stars in the universe, and every star is a real number, there can be infinitely many stars. That means there had to be more infinities between the two infinities. But where could they be? Here's where Cantor made his most famous blunder. He appealed to common sense and said that since infinite is bigger than 10 to the 30th power, it must have an infinite number of subsets. That common sense argument made sense to Cantor and some of his contemporaries. But it didn't sit right with others like Paul Cohen, who thought it shouldn't be possible to have an infinite number of infinities. Over the years, Cohen convinced himself and several of his colleagues that Cantor's continuum hypothesis was formally undecidable. In other words, it couldn't be proven or disproven using current mathematical laws. Cohen spent decades trying to prove his claim, but he never succeeded. In 1963, Paul Cohen died believing that a continuum hypothesis was formally undecidable. But in 1963, Paul Cohen died believing that the continuum hypothesis was formally undecidable. 4 years later, Paul Cohen's widow and a mathematician named Paul Cohen discovered that George Cantor had already proved it. While working at the Institute for Advanced Study in Princeton, Cantor had indeed figured out that there were even more infinities between those two. And in 1963, Paul Cohen published the proof. Cantor's continuum hypothesis changed math forever. It led to the development of new fields of study and inspired countless papers on the foundations of mathematics. And while none of us are likely to personally stumble across an infinite set of infinities in our day-to-day lives, Cantor's ideas have had wide-ranging impacts. For example, algorithms rely on the ability to make decisions based on probabilities, which in turn relies on the continuum hypothesis. So does our understanding of wave mechanics and quantum computing. And Cantor's insights also helped inspire computer scientists who needed to model things that could theoretically go on forever, like the internet. Computer scientists define a Turing machine as a theoretical machine that can perform any calculation that can be done by an algorithm. Since the set of natural numbers that positive integers can theoretically go on forever, computer scientists needed a way to model that in their calculations. And that's where Cantor's continuum came in handy. The continuum provided the basis for the concept of limit, which says that when dealing with potentially infinite processes, we can approach a value without actually ever reaching it. Limits allow us to model systems that evolve over time, like radioactive decay or the spread of a rumor through a population. And limits are used in virtually every field of science today, including physics, chemistry, biology, economics, and engineering. And that's just a small sampling. Cantor's continuum hypothesis has influenced everything from the philosophy of science to the ethics of artificial intelligence. And yet, when Cantor first proposed his continuum hypothesis, he met with a lot of resistance. Not only did his contemporaries not understand his proof, but they also rejected his ideas about infinity. A lot of mathematicians thought infinity was just a tool that we use to describe situations that are very large but still finite. They thought Cantor was making a category error by asking whether there were actually different sizes of infinities. One mathematician complained that Cantor's continuum hypothesis was about as meaningful as asking whether the continuum of real numbers has the same number of points as the continuum of blues. But Cantor wasn't deterred. He continued to study set theory until his death in 1967. And in that time, he fundamentally changed the way mathematicians think about infinity. These days, Cantor's continuum hypothesis is generally considered to be one of the most important advances in 20th century mathematics. And it's a testament to Cantor's brilliance that something so abstract has had such practical applications. But that's not the only thing Cantor's story illustrates. It also shows us that even brilliant mathematicians can make mistakes. In fact, they can make huge mistakes, ones that change the course of mathematics. But sometimes those mistakes can lead to even bigger insights. Thanks for watching this episode of SCI Show. This Minute Earth video was brought to you with the help of our patrons. Our patrons also get access to a whole bunch of perks like blooper reels and a patron-exclusive podcast. You can check out the perks and join our amazing community of supporters at our support page.